Okay, let's get right into it. Have you ever been stuck on a problem that just feels like a tangled mess? Where everything is connected and changing one thing messes up something else? Well, it turns out there's a beautifully simple system for turning that kind of chaos into perfect clarity.
We've all been here, right? Trying to juggle a bunch of different rules and conditions all at once. The great news is, there's a method to the madness. We're going to virtualize a puzzle, basically turning a real-world headache into a clean, abstract system that's actually easy to solve.
So here's our puzzle for today. It seems pretty straightforward, but it's got all the pieces of a much bigger, much more complex problem. We're trying to find two unknowns. The number of bags, we'll call that X, and the number of boxes, which we'll call Y.
All right, first things first. We have to translate this story into the universal language of math. This is the absolute key first step in creating that virtual version of our problem, something a computer can understand and solve in a blink. And just like that, the story becomes a set of instructions. The top equation is our apple count. 2 apples from every bag plus 6 from every box gives us 20 total. And the bottom one? Well, that's the same deal for the bananas. The entire problem captured in just 2 lines of code, basically. So what we've just made, this thing, it actually has a name. It's called a system of linear equations. All that means is it's a bunch of equations that are all tied together by the same variables. In our case, good old X and Y. This is the bedrock for everything we're about to do.
Okay, this is really cool. There are 2 totally different ways to see this system. On the left, you have the row picture. Each equation is just a line on a graph, and the answer, the solution, is the single point where those 2 lines cross. But on the right, in the column picture, it's more like we're asking, how many bag recipes and box recipes do we need to combine to get our final pile of fruit? 2 different views, but they all point to the exact same answer.
So those equations are great, but you know what? We can make our virtual model even cleaner, even more powerful. Let's take the next step and pack this whole system into something called a matrix. I mean, think about it. The X's and Y's, the plus signs, the equal signs, they're just scaffolding, right? They're always there. The real information, the stuff that changes from problem to problem, is in the numbers. So, what if we just stripped everything else away?
Well, we can. And that's exactly what a coefficient matrix is. We literally just pull out the coefficients, the numbers right next to the variables, and pop them into a nice, neat grid. We've just boiled the problem down to its essential numeric DNA.
I love this analogy. Think of that matrix as a machine. You feed it your inputs on one side, how many bags and boxes you have, and it churns through a calculation and spits out the results on the other side, the total number of apples and bananas. Okay, to finish our virtual model, we just need one more step. We take our coefficient matrix and we augment it, fancy word I know, by sticking on one more column for the totals. Now, every single important number from our original story is locked into one elegant package. And there it is. Look at that. That is our entire fruit puzzle, but in its purest form. No X's, no Y's, no clutter at all. Just the raw information, perfectly organized and ready for us to solve.
So, now that we've set up the game board, it's time to actually play. We're going to solve this thing using a simple game with a very clear set of rules. The method is called Gaussian Elimination, and it's one of the most powerful tools in all of mathematics.
And hey, don't just take my word for it. The legend himself, Gilbert Strang, who's a huge inspiration for this whole explainer, says the idea is deceptively simple. Our whole goal here is just to make our matrix simpler and simpler, one move at a time. So, what are the rules of the game? They're super easy. First, we pick a pivot. Let's start with that 2 in the top left corner. Now, our mission, should we choose to accept it, is to use that pivot's entire row to strategically wipe out the number right below it, to turn it into a 0. Okay, here's the key move. Our target is that 4. We want it gone. We want it to be a 0. How can we use the 2 above it to do that? Well, if we multiply that entire top row by 2, the 2 becomes a 4. And then we can just subtract the top row from the bottom row. 4 minus 4 is 0. Let's do it. And there it is. Look at that. A 0, right where we wanted it. Now, of course, we had to do the same thing to the entire row. So the 8 became a -4, and the 28 became a -12. But who cares? The important thing is we've made the puzzle simpler. Now we can translate that new bottom row back into English. What's it telling us? It says 0 times the number of bags, plus -4 times the number of boxes equals -12. Wait a second, that's just -4y equals -12. We can solve that in our heads. Y must be 3. Boom, we found the number of boxes.
And once we know y is 3, the rest is a piece of cake. We just plug it back into the top equation to find that x is 1. The solution was hiding in there the whole time. The answer? 1 bag and 3 boxes. Puzzle solved.
Okay, so that was a fun little puzzle. But why does any of this matter? Why go through all that trouble? Well, let's zoom out to the bigger picture and see how this little game is used to solve some of the biggest problems you can imagine. Our problem had 2 equations, right? Which we saw as 2 lines crossing at a single point. But what if you have 10 equations with 10 unknowns? As Gilbert Strang puts it, that's like trying to find the one single point where 10 different 9-dimensional planes all intersect in 10-dimensional space. Yeah, try to picture that.
It's pretty much impossible to actually visualize, but this image gives us a little hint in 3D. The amazing thing is, the math works exactly the same. The game of elimination we just played, the game with the pivots and the zeros, that's the very tool that lets us find that one single solution point no matter how many crazy dimensions we're dealing with.
And believe me, this isn't just theory. This exact method is humming away behind the scenes in so much of our daily lives. It's how your computer renders amazing 3D worlds in video games. It's how internet traffic gets routed efficiently. It's at the heart of machine learning, economic models, and it's even how your phone's GPS knows exactly where you are in the face of the Earth.
So, we started with the simple fruit puzzle, we virtualized it into a clean, powerful matrix, and then we solved it by playing a simple game. A game that scales up to solve problems the size of planets. So that really just leaves one final question for you. What messy, real-world system in your world would you want to virtualize and solve next?